In this lesson we will discuss the physical factors that determine the capacitance of a capacitor. Capacitance is defined as the ability of a device to store an electric charge. It can also be defined as the ability of a device to oppose any change in circuit voltage. Capacitance is that property of a capacitor which opposes voltage change. Electric energy can therefore be stored in a capacitor. Electrons are held within a capacitor, and this, in effect, is stored electricity. It is also known as an electric potential or an electrostatic field. Electrostatic fields hold electrons. When the accumulation of electrons becomes great enough, the electric potential is discharged. The same process occurs in nature. Clouds build up electrostatic fields, and the discharge process is observed as lightning. The two parallel plates separated by a distance and connected to a source as shown in the figure represents a capacitor with vacuum as a dielectric. A dielectric is the insulator which separates the two conducting surfaces. The letter symbol for capacitance is C, and its units is the farad, F, named after the English scientist Michael Faraday. The relationship between the voltage charge and capacitance is V is equal to minus Q coulombs divided by C in farads. The negative sign indicates that the voltage V across the capacitor balances the source voltage E. Using Kirchhoff's voltage law, we obtain E1 plus V equals 0, or E1 is equal to minus V, which is equal to Q divided by C, which then results in C equals Q divided by E1. We know that permittivity of free space is the Greek letter E for epsilon, which is equal to D divided by E, or Q divided by A divided by E1 divided by D, which is equal to Q divided by E1 times D divided by A. Substituting C equals Q divided by E1 gives epsilon equal to C times D divided by A, or C is equal to E sub 0 times A divided by D. Therefore, capacitance is directly proportional to the area of the plates, but inversely proportional to their distance of separation. Since we know from an earlier lesson that Q is equal to I times T, current is expressed as rate of change of charge with time as shown. I is equal to delta Q divided by delta T. I, therefore, is equal to C times delta V divided by delta T, or I divided by C equals delta V divided by delta T, the rate of change of voltage. When the vacuum between the plates of a capacitor is replaced by an insulating material, the capacitance is increased. The relative permittivity, also referred to as dielectric constant, is equal to the ratio of the capacitance of a capacitor with an insulating material as a dielectric to its capacitance with vacuum as a dielectric. The symbol for relative permittivity is mu sub r. Thus, mu sub r is equal to C for the insulating material dielectric divided by C for the vacuum dielectric. And capacitance is equal to E sub 0 times E sub r times A divided by D in farads, where E sub r is the permittivity of the dielectric material. So E sub 0 is equal to 8.85 times 10 to the minus 12th SI units. Consequently, absolute permittivity, E, is equal to E sub 0 times E sub r, or D, flux density, divided by E, the field density, from which C is equal to E sub 0 times E sub r times A divided by D, which equals E times A divided by D. Let's look at an example. A capacitor consists of two sheets of metal foil, each side of which has an area of 1,000 square centimeters. The distance of separation between the sheets is 0.2 millimeters, and the type of dielectric is paper with a relative permittivity of 3. Calculate the value of the capacitance. If the capacitor is charged to 300 volts, what are the values of A, charge stored, B, flux density, and C, electric field intensity? The capacitance is equal to E sub 0 times E sub r times A divided by D, or 0.013 microfarads. To solve for this charge stored, Q is equal to C times E, which is equal to 3.9 microcoulombs. Electric flux density is equal to Q divided by A, or 39 microcoulombs per meter squared. Electric field intensity is equal to V divided by D, or 1.5 times 10 to the 6 volts per meter. The table shown illustrates dielectric constant or relative permittivity values for selected dielectric materials. The ability of a particular dielectric to withstand a high electric field intensity is termed its dielectric strength and is expressed in kilovolts per millimeter. Some dielectric strengths of common materials are indicated in this table. Each capacitor possesses a voltage rating as recommended by its manufacturer, depending on its insulator's dielectric strength. This is called the DC working voltage, written as WVDC, and is a maximum DC voltage that can be applied across the capacitor without causing a breakdown of the dielectric. The voltage rating is a significant factor since it determines the physical size of a capacitor. A 0.2 microfarad capacitor with a 1 kilovolt rating will be larger than a 0.2 microfarad capacitor with only a 200 volt rating. Thus, the voltage rating of a capacitor may be compared with the power rating of a resistor and the current rating of an inductor. Also, in AC circuits, since the effective value, approximately 70% of the peak value, is given, a capacitor whose rating is 200 working volts DC might break down when an AC voltage with an effective value of 200 volts is applied across it. Capacitors may be of the fixed or variable type. Typical symbols are illustrated.